Hello everyone. Welcome to part 2 of my presentation about quantum correlations. In part 1, I took the time to explain some basic concepts and hopefully reduce the amount of confusion on this topic. In part 2, I want to switch the focus to more advanced aspects, starting with quantum monogamy. Bell tests are usually performed by combining 4 joint experiments. For example, we need to determine the rates of coincidence between A and B measurements, then between B and C, then between C and D, and finally D and A. The question is, why do we need so many steps? Why can we not make 4 entangled quanta instead of 2 and measure all the properties at the same time? This would make the experiment easier and simplify the interpretation. Indeed, many loopholes would be automatically closed. So why not make a Bell test with 4 entangled quanta instead of reusing pairs so many times? For a long time, the answer could not be provided because 4 quantum entanglement was practically not available. Yet, starting about 2 decades ago, this problem was solved. Nonetheless, Bell violations with more than 2 entangled quanta were never demonstrated. Instead, by a curious historical coincidence, we started getting more and more theoretical proofs that single-shot experiments with Bell violations are impossible. This phenomenon is known as monogamy of quantum entanglement. In other words, entangled quanta violate the Bell inequalities in pairs and only in pairs. No quantum is willing to exhibit such correlations with 2 partners or more, or at least not at the same time. Let us first try to understand this phenomenon the wrong way. Suppose that quantum non-locality is real, and we are conducting joint experiments with 2 entangled quanta at a time. In this case, one and the same quantum of Alice must display a plus outcome if Bob selects property B1, but magically switch to a minus outcome for the same exact measurement if Bob decides to measure B2 instead. This may sound spooky, but it is not very hard to imagine. Still, let us now suppose that Alice and Bob decided to measure all of these 4 properties at the same time. They prepare 4 entangled quanta, and Alice gets to keep 2 of them. She can use one of them to measure A1 and the other A2. Bob also gets 2 quanta to measure B1 and B2. So we use a different quantum for each of the 4 measurements. This means that Alice can only register one value for A1, and this one value has to be counted in coincidence with both B1 and B2. As you can see, it is no longer possible for Alice's events to flip in response to Bob's choice of measurement, and therefore, Bell violations are no longer possible. As we saw in part 1 of this presentation, Bell violations require incompatible observables. If we force all of the events to be simultaneous, we get joint distributions, and Bell violations are impossible. This is exactly what happens if we try to make a one-shot Bell experiment. Yet, this is where things become really interesting. In theory, we should be able to achieve quantum Bell violations even with ideal measurements where detection efficiency is 100%. This means that we can use the same events in any possible experimental protocol. So, when Alice measures her 2 quanta, she gets the same exact observations that would be detected if Bob also measured his quanta at the same time. Unfortunately, this creates a problem. You see, if Bob makes no measurement, then Alice's events must be able to violate the CH-SH inequality because they are entangled. Yes, she would have to repeat 4 pairwise measurements, but the point is that her correlations are always going to be such as to enable violations. In contrast, when Alice and Bob count 4 quanta at the same time, then Alice's coincidences must suddenly be different because they cannot be used to achieve Bell violations. We now have quantum monogamy. So Alice makes the same exact measurement no matter what Bob does, yet her observations cannot be the same in both cases. Furthermore, we cannot assume that Alice's quanta are maximally entangled while Bob's quanta are not, because the same argument applies in both arms of the experiment. No matter how we switch it, some quanta have to change their behavior without a physical reason. A possible solution, and indeed a popular one, is to say that quantum non-locality is crazier than we thought before. Quantum systems must behave as if they know how many measurements are made at any distance from each other. Yet, this does not work because we end up contradicting a basic principle of quantum mechanics. Allow me to explain. When Alice and Bob make one measurement each, we can see why quantum behavior is non-signaling. Alice gets one event, and she has no idea if her event is correlated with Bob's event or not. There is nothing verifiably different about her event, whether or not Bob makes a measurement at the same time. Only later, when the experiment is over, Alice and Bob can come together and reconcile their event records to calculate coincidences. So, Alice and Bob cannot send messages faster than light to each other. However, in the quantum monogamy case, we have something different. Alice measures 2 quanta at a time, and she can use these 2 quanta to derive coefficients of correlation for different pairs of observables. Moreover, these coefficients are such that they violate Bell's inequality. Nonetheless, quantum theory prohibits Bell violations if Alice and Bob make their measurements at the same time. In short, we should have a locally observable difference between 2 scenarios depending on Bob's choice of action. Alice gets one set of coefficients by herself and a different set of coefficients if Bob joins the experiment. Recall that we assumed a measurement efficiency of 100%. Therefore, Alice is supposed to detect the same quanta in both scenarios. Accordingly, it looks as if Bob can send messages to Alice simply by choosing to measure or not to measure his quanta. This means that faster than light communication should be possible. Yet we know that quantum mechanics is a no-signaling theory and does not allow for this kind of behavior. Some people have proposed avoiding this paradox by postulating a fundamental limit on entanglement. In other words, nature would never allow us to entangle 4 quanta such as to arrive at this paradox. Yet, this limitation is not based on anything concrete in quantum theory. It may sound loosely similar to the no-cloning theorem, but cloning involves measurements of quantum states after creation. Quantum entanglement is about the process of creation itself, and it is very well known to be immune to the no-cloning principle. On closer inspection, this paradox is not due to the rules of quantum mechanics. It is due to the decision to invent quantum non-locality. For a long time, it seemed that quantum non-locality is harmless because it was described as non-signaling. Yet, what we see in the case of 4 quantum entanglement is that this assumption was wrong. As we discover more and more complex quantum phenomena, it becomes more and more difficult to reconcile non-local interpretations with the principles and concepts of quantum mechanics. In short, quantum non-locality does not work. On the other hand, I have already shown you that Bell's theorem is a false argument. Therefore, we do not need to approach this problem with spooky assumptions. Instead, we can just treat Bell violations as a combinatorial problem. Hence, if we have properties that exist at the same time, then we can also detect them at the same time. In this case, we expect to obtain compatible coefficients of correlation, and Bell's inequality must always be obeyed. In contrast, when we have mutually exclusive properties, we cannot expect them to manifest at the same time. Instead, they have to become real one after another in sequence. For this reason, when we work with staggered events, we can get incompatible pairings. For example, as you can see in this drawing, we can have a series of events at different time coordinates, and we can use narrow coincidence windows to isolate only two at a time. In this case, property A1 is expressed at time coordinate T1, and it falls in the same coincidence windows as B1. Later, we get coincidences between B1 and A2, followed by A2 and B2. Yet, notice that B2 is now closer in time to a different event for A1. If we keep the window of coincidence fixed, then we get a coincidence between B2 at T4 and A1 at T5. In short, even if we have a blind method for getting coincidences at different points in time, we are going to get incompatible combinations between different pairs of events. Indeed, our combinations can be fully incompatible in this case, leading to maximal Bell violations. Yet, notice that we are only able to do this because we make our measurements in pairs. If we tried to achieve the same result with larger windows of coincidence, such as to include more than two events, then we would fail. For example, let us bring back our setup with a spinning arrow. When we have a so-called Alice event, such as A1, we can make a paired observation with any Bob event B1 or B2. However, these events are adjacent to the sector occupied by the arrow. We use a short window of coincidence, and maximal Bell violations are possible. Furthermore, we can use two copies of the same system to make joint measurements at a distance. Alice measures A1 or A2, Bob measures B1 or B2. As long as the two systems are synchronized and the window of coincidence is narrow, they will achieve Bell violations. Yet, suppose that we decide to make 4 copies of the same system. Alice can get 2 copies in order to record 2 values at the same time, one for A1 and one for A2. Bob gets the remaining copies to measure B1 and B2. Yet, we need to increase the window of coincidence such that all the events can be observed in one shot. As a result, we now break the flow of events into bunches of 4 detections. Suddenly, our properties are reorganized from this pattern to this pattern as if they are jointly distributed. We can only calculate coefficients of correlation based on our record of events. Yet, we always record 4 events at the same time. This means that we have to use the same values of A1 for coincidences with B1 and for coincidences with B2. The same restriction applies to all the other combinations between our variables. As a result, we get combinations that are compatible with each other and we are no longer able to achieve Bell violations. The important question to ask is, why did we get this result? Is it because we have spooky action at a distance? Is it because we have incomprehensible weirdness? No. We are simply choosing to group the same events in different ways, and this is why we achieve different coefficients of correlation. Our events do not know anything and do not change in any way. Instead, our method of accounting is different, and therefore the balance of event combinations is also different. In conclusion, Bell violations do not require metaphysical explanation. This is a combinatorial problem. When physical events do not happen at the same time, they can be combined in incompatible ways. As a result, they can produce Bell violations. However, this trick is only possible when we record our coincident events in pairs. If we increase the number of simultaneous coincidences, then we lose the ability to make such combinations. Consequently, the so-called quantum monogamy is also a combinatorial problem. There is no mystery to explain, and there is nothing here that challenges the limits of human understanding. And with that out of the way, we have reached the most interesting part of our discussion. Quantum theory is supposed to be strange because it predicts violations of Bell's inequality. Nonetheless, quantum correlations have a limited span as well. In the case of the CH-SH inequality, they can go beyond the Bell limit, which is S equal 2, but they cannot exceed the so-called Tsirelson bound, which is equal to 2 square root of 2. Because of this, many scientists are puzzled. Why is this happening? Previously, this was just an open problem given widespread assumptions of non-locality. In other words, if quantum entanglement can use magic to violate Bell's inequality, why can it not use the same magic to achieve maximal violations? Yet, now we know that Bell violations are local all the way to S equals 4, and so this problem is even more intriguing. If Bell violations are possible in classical mechanics without limit, then why is it that quantum theory can only produce violations below Tsirelson's bound? As you will see below, quantum measurements correspond to alternative transformations of input states. While quantum amplitudes are hard to interpret, we can use classical electromagnetic waves to help our intuition. For example, we can prepare a depolarized optical projection, which we then divide with a polarizing beam splitter. The energy of a wave is proportional to its amplitude squared. Accordingly, we can use the parallelogram method of vector decomposition, as well as Pythagoras' theorem, to predict the amount of energy that is expected in each output. So, if we count quanta or measure classical beam power, our outputs are supposed to be proportional to the cosine squared of the new angle of polarization. This rule is also known as Malus's law. To get multiple observables, as needed for a Bell test, we have to split one and the same input projection in many alternative ways. I think it is helpful to understand this process in more general terms. So let us review some basic features of energy redistribution. For starters, imagine a billiard ball that is rolling on a smooth table. Due to this motion, we know that the ball has a measurable quantity of momentum in this direction, as suggested by this blue arrow. So, if the ball were to experience a perfectly elastic head-on collision with another billiard ball with equal mass, then it can transfer up to 100% of its energy to the second ball. Yet we can also have a collision at an angle. In this case, we can ask how much energy can the white ball transfer to the red ball. As a reminder, momentum is a vector quantity proportional to the velocity vector. However, energy is proportional to the square of velocity and is a scalar quantity. So if we want to derive our pattern of energy redistribution, we need to do vector decomposition, and then we need to apply Pythagoras' theorem. For the purpose of our discussion, the important consequence is that we get a cosine squared relationship between input and output quantities. Hence, if we have a diagonal collision between a moving ball and a stationary ball, we can expect that the energy of the red ball will be equal to the energy of the white ball times the cosine squared of the angle of 45 degrees between the two velocity vectors. This means that the red ball will receive a maximum of 50% of the input energy. However, momentum conservation entails that we must also have another component vector oriented in a complementary direction. The vector sum of our components is equal to the input vector. In this case, we know from practical experience that the first ball is likely to experience a deflection along the opposite diagonal. Therefore, the white ball will carry the remaining 50% of its input energy in this new direction. Let us take a moment to appreciate this pattern of physical interaction. Billiard balls can experience numerous types of elastic collisions. As a result, their motion can suffer alternative transformations that are mutually exclusive. For example, the energy can be redistributed 15 to 85, 50-50, or any other combination. Yet only one of these transformations can happen at a time. We only have 100% of energy at the start, and all of it is redistributed in the event of a collision. More importantly, the geometry of elastic collisions between billiard balls with equal mass is such that we can use the cosine squared law to predict the final result in each alternative scenario. This rule has a very interesting consequence, at least for the purpose of our discussion. Let us imagine again that we have a billiard ball rolling on a pool table. At some point, it collides with another ball and deflects it by 22.5 degrees. This means that it will transfer 85% of its original energy. Eventually, the second ball collides with yet another ball, producing a similar deflection of 22.5 degrees. This means that the final billiard ball is now moving at 45 degrees from the original input direction, and it can receive as much as 72% of the original amount of energy. However, we saw just a minute ago what happens when we have the same final deflection from a single collision. The relative angle between input and output is also 45 degrees, but we have a much bigger drop in transferred energy. The cosine squared of 45 degrees is 0.5, and so the final ball is only able to receive 50% of the input energy. Surprisingly, it is not possible to express one deflection at 45 degrees as the sum of two deflections at 22.5 degrees. In other words, the cosine squared law is nonlinear and it produces radically incompatible outcomes. It is not possible to explain such values in terms of pre-existing properties. Moreover, because these alternative properties are incompatible with each other, they lead to coefficients of correlation that are also incompatible with each other. As a result, they can produce combinations that lead to violations of Bell's inequality. Please note that we are not doing anything magical here. This is simply the natural way to transfer and redistribute energy in some types of classical interactions. Yet, I hope that you recognize these patterns because they are very common in quantum mechanics and classical optics, especially in the case of polarization measurements. For example, suppose that we have a classical beam of light polarized in the vertical plane. We can mark this plane of polarization as 0 degrees. We can then pass our beam through a linear polarizer at 22.5 degrees. The result is predicted by Malus's law, meaning that a maximum of 85% from the input beam power will be detectable in the transmitted path. Of course, this is the same cosine squared law applied to an angle of 22.5 degrees. Furthermore, we can add another polarizer at 45 degrees, and the beam will lose an additional 15% of the remaining energy. Therefore, the final amount of irradiance will be 72% of the input quantity. In contrast, if we remove the first polarizer and leave just a second, aligned at 45 degrees, then our beam will be able to transmit only 50% of its input amount of energy. It seems surprising that we have the same plane of polarization at the end in both cases, but the amount of leftover energy is so different. How can this be? If we remove one filter, it seems that we should have more transmitted energy, not less. The simple answer is that we are not filtering pre-existing components from the input beam. The evidence is clearly incompatible with such an assumption. Instead, we must assume the reality of alternative transformations during the interaction between the beam and the polarizer. This is the same phenomenon that we examined in part 1 with the rope. To sum up, Malus's law is just a special case of a wider principle that governs energy redistribution in classical mechanics. Billiard balls can either collide with a small deflection or with a large deflection. It is not possible for both scenarios to be real at the same time. Yet, momentum conservation, as captured by vector decomposition, entails the projection of disproportionate quantities for each setting. Linear changes in the angle of interaction correspond to non-linear changes in energy redistribution. By implication, incompatible transformations produce incompatible coefficients of correlation if measured in pairs. This is why they can violate the Bell inequalities. In other words, the source of this incompatibility is a natural process that is local to the transformed system. We do not need external influences for this to take place. And here is another crucial detail for our discussion. It was shown by Tsirelson and by many other researchers since then that Malus's law has a limiting effect on the range of correlations that can happen in a Bell experiment. As we have seen above, joint distributions allow for no contradictions between coefficients. Therefore, the limit of correlation is S equal to for the CH-SH protocol. In contrast, we have just seen that Malus's law allows for contradictory properties in alternative scenarios. This is why Bell violations become possible. Nonetheless, these contradictions are only possible as long as they also obey the cosine squared rule. So we still have a rigid restriction, just not as low as Bell's limit. Therefore, if we have alternative physical transformations and the cosine squared law is obeyed, then we can get Bell violations, but we cannot exceed the limit of S equals 2 root 2 for the CH-SH protocol. As shown in the first part of this presentation, Bell's inequality applies to the properties of single classical systems. Therefore, correlations between two copies of the same system must also obey the inequality. Likewise, sequential properties of a single system can produce maximal Bell violations. This is why we can also get such violations with two correlated systems. And finally, for the same exact reason, we can get quantum-like patterns of violation in the case of alternative transformations with energy redistribution. Even in the case of simple collisions, it is one and the same billiard ball that can be deflected in several incompatible ways. Yet only one of these scenarios can happen at a time. This is why we can get mutually exclusive properties. If we could measure these alternatives in parallel universes in pairs, we would be able to achieve correlations that violate Bell's inequality. However, we cannot do that. Instead, we can make identical copies of our systems in a single universe. Then we can use such pairs of correlated systems to confirm the rate of coincidence between alternative properties. In our models on paper, these correlations follow directly from the geometry of vector decomposition. Ergo, the corresponding physical interactions in real life express the same pattern locally. They simply express the principle of energy conservation during binary redistribution. The only problem with this explanation is that I used systemic examples. You see, the momentum of a billiard ball as a whole is divided 85 to 15 in a single collision. Likewise, a macroscopic classical beam is also instantaneously divided 85 to 15 in a polarization experiment. However, this is not what we see in quantum mechanics. Instead, we have a statistical process where millions of events are distributed according to these systemic rules. In other words, we cannot expect Bell violations in the statistics of collisions between many billiard balls. Instead, the momentum of a single ball treated as a system is where we can see such patterns. So, a population of quantum events expresses the same pattern of behavior as a single billiard ball or a single high-intensity optical pulse. In other words, there is a mystery behind quantum Bell violations, but this is not the mystery of non-locality. As suggested by Richard Feynman, there is only one mystery in quantum mechanics. This is the mystery of unobservable wave superposition expressed in the distribution of observable discrete events.
My goal is to give you a visual understanding of this process, and I think that the Mach-Zehnder interferometer is particularly useful in this regard. As you can see in this diagram, we can create an optical rectangle by combining two non-polarizing beam splitters and two mirrors. Imagine that we have a collimated classical beam entering the first non-polarizing beam splitter. The input projection is split 50-50, and then each path is reflected by the mirrors M1 and M2, such as to recombine at the semi-reflective surfaces of the second non-polarizing beam splitter. Let us take a closer look at this mechanism because the details are important for our discussion. Note that our beam splitter is non-polarizing and the two output projections are practically identical to each other. As you can see here, half of the input beam is reflected. Then it bounces off the mirror M1 and arrives at the second non-polarizing beam splitter. At this point, we get another 50-50 split, which means that we can expect 25% of the input radiation in each output channel. At the same time, the other half of the input beam is transmitted at the first beam splitter. As you can see, it is reflected by the second mirror and arrives at the bottom side of the second beam splitter. As long as the other beam is absent, we expect a 50-50 split again, which corresponds to 25% of the input projection in each output path. The question is, what happens if the two projections from the first beam splitter arrive at the second beam splitter at the same time? The answer is that we have two coherent beams overlapping, and therefore we expect interference. However, the details of this process are highly contextual. Many patterns are possible. Yet, the relevant configuration for our discussion happens when all of these conditions are met. In particular, if the two paths inside the interferometer are equal, then we see the following. 100% of the input radiation is detected in the eastbound channel, and no radiation at all is detected in the northbound channel. The well-known explanation is that a non-polarizing beam splitter has two semi-reflective surfaces at this diagonal interface. For reasons that we do not need to discuss here, the top semi-reflective surface has a volume with destructive interference, which is why we get a dark channel in this direction. At the same time, the bottom semi-reflective surface has a volume with constructive interference, which is why we get a bright channel in this direction. Yet, here we need to digress a bit for the sake of conceptual clarity. Classical interference is often perceived as incompatible with quantum interference because of a regrettable misunderstanding. In particular, some people assume that classical waves go through each other unperturbed. Therefore, interference is often interpreted as a macroscopic illusion. For example, destructive interference is interpreted to show that two coherent components cancel each other's observable qualities. We still have two beams propagating in this channel, but we are not able to detect them. Likewise, we should still assume that we get 50% of input radiation in this channel, except that amplitudes overlap in phase, and we get the appearance of strong radiation. On closer inspection, this interpretation cannot be correct. You see, energy conservation requires the unobservable energy to go somewhere as if it is absorbed. In the case of destructive interference, we should get extra heat or some other way to account for the missing energy. More importantly, we should only have 50% of all the energy in the bright channel. In actuality, we never get any trace of missing energy in the dark channel, and we always detect 100% of the input energy in the bright channel. For example, if we put a power meter in the path of the input beam and record 1 milliwatt here, then we get roughly the same amount if we move the same power meter to this output channel. So it is easy to verify that we do indeed get all the energy of the input beam in a single output path. In short, the correct interpretation is that we do not have component cancellation. Instead, we have energy redistribution. When the electromagnetic waves are out of phase at the top semi-reflective surface, we should imagine that they hit a closed gate and become redirected into the bright channel. As a result, we see no radiation in the north channel because nothing is propagating that way. Instead, all the energy is detectable in the east channel because that is the only available way for it to flow. Indeed, if we make this interpretive adjustment, then we gain continuity between classical and quantum phenomena. As it is known, quantum theory describes destructive interference as a region where the probability of detecting a quantum drops to zero. Yet, this is compensated by a matching increase in the probability of finding the same quantum in the area with constructive interference. Accordingly, the default setting of a perfectly aligned Mach-Zehnder interferometer is that we get no radiation in this channel, and all the input radiation is redirected into this channel as a result of coherent interference. Furthermore, we can mount a step stage under one of our mirrors and use it to change the total length of this path by a few nanometers at a time. You see, if we pull this mirror a little bit backward, then the blue path becomes a little bit longer. Therefore, radiation in this path is going to arrive at the beam splitter with a delay. Yet, the phase delay between overlapping output beams automatically changes the details of interference. In other words, we get 0% in this channel and 100% in this channel because the paths are perfectly equal and the phase delay is 0. However, if the phase delay is increased to 90 degrees, then the top beam is 1/4 of a wavelength behind the bottom beam. This means that we get a new pattern of interference such that 50% of the input energy arrives in the northbound channel and 50% arrives in the eastbound channel. In other words, increasing the phase delay works as if the output radiation is redistributed back from this path into that path. Furthermore, if we increase the phase delay to 180 degrees, then we achieve a complete reversal of the initial pattern of interference. The two components are now perfectly out of phase in the east channel, and we get 0% of the input radiation in this path. Instead, they are suddenly in phase in the north channel, and 100% of the input energy can be detected in this output path. At this point, some of you might be wondering, why do we need to spend so much time talking about Mach-Zehnder interference? How is this relevant for the problem of quantum correlations? The answer is that the pattern of energy redistribution in a Mach-Zehnder interferometer is governed by a cosine squared rule, just like the other examples that we considered before. For example, a phase delay of 45 degrees is equivalent to a polarization difference of 22.5 degrees, and a phase delay of 90 degrees is equivalent to a polarization difference of 45 degrees. This means that we can use the Mach-Zehnder interferometer to explore the same type of behavior that we saw in typical quantum experiments. Yet the advantage is that we get a visual classical explanation for the local mechanism behind such correlations. As a quick reminder, if the phase delay is 90 degrees, then 50% of radiation from the bright channel will be redirected into the dark channel. However, if the phase delay is 45 degrees, then only 15% will be redirected from east to north. Clearly, we get two profiles that cannot be reconciled with each other because 45 degrees plus 45 degrees is 90 degrees, but 15% plus 15% is not 50%. Yet, what is the source of this behavior? It should be easy to notice that we obtain any phase delay that is necessary by adjusting the position of the staged mirror. But what exactly is happening when we displace the mirror? The answer is that we change the pattern of superposition in the plane of overlap between the two projections. Specifically, this is taking place at the semi-reflective surfaces of the second beam splitter. The nuance here is that we change a system-level property. We manipulate the redistribution of energy in the beam as a whole. Yet, this macroscopic manipulation has a microscopic effect. After all, we cannot redistribute the energy of a beam as a whole without redistributing the constituent elements of the same beam. Though, before we move forward, we need to clarify another ontological detail. We know that optical projections are made of photons, but we do not know much about these types of quanta. Nonetheless, our goal is only to show that classical explanations are in principle possible for quantum correlations. And so, for the purpose of our discussion, we only need a simple model in which wave patterns determine the distribution of discrete objects. For example, let us imagine a big ripple tank in which water waves produce a double-slit interference profile. If this pattern is stable over time, we can have surfers on these waves one at a time. It does not matter what slit they take and what trajectory they follow. The only important detail is that surfing is impossible without waves. The water level is always flat in the areas with destructive interference. Therefore, we cannot expect to detect any surfers in these regions. Instead, we can expect the probability of detection to grow as the net amplitude of the wave profile is getting larger. This means that the statistics of surfer distribution is entirely determined by the macroscopic details of wave interference. If we wait long enough, we can obtain a distribution of surfers in the plane of detection that is a perfect reflection of the distribution of wave amplitudes in the same plane. In a similar manner, we can interpret the behavior of optical projections in a tunable Mach-Zehnder interferometer with a pilot wave model. We can assume that we have a stable wave interference pattern and that quanta propagate as if they surf invisible waves. For example, we can imagine how every single surfer enters the interferometer. It takes either the transmitted path or the reflected path, and then it reaches the second beam splitter. As you can see, it makes no difference when the surfers enter the interferometer, which path they take, or how they travel inside each path. The only consequential detail is the net state of the pilot wave at the semi-reflective surface of the second beam splitter. The thing to keep in mind is that our surfer can only cross this plane once. This happens in an instant. Therefore, we cannot have two settings of phase delay at the same time. If the net state of the pilot wave has destructive interference in the northbound channel, then the probability of detecting a photon in this direction is 0. Instead, the probability of a detection event in the eastbound channel is 100%. More importantly, we can change the phase delay between the two projections at will. So, if the phase delay is changed to 45 degrees at the instant when the surfer arrives, then the probability of exit in the east channel is no longer 100%. Instead, we have a probability of 85% of exit in the eastbound channel and 15% of exit in the northbound channel. Let us pause for a moment here in order to consider the wider picture. Supporters of quantum non-locality insist that Bell violations defy human understanding. It is not possible to find a local explanation for such a process. However, we can see here that it is in fact the opposite. We have a systemic process of interference. Two wavefronts arrive at the business plane of a beam splitter and overlap. At this exact moment, they are either in phase or out of phase. Only one of these profiles can be true, and we can decide which one of them is true by changing the position of this mirror. This means that we always have a choice between several patterns of behavior for each individual surfer in a Mach-Zehnder interferometer. If we keep the phase difference at 0, then the output probability distribution is 0 to 100. If we switch the phase delay to 45 degrees, then we get a pattern of 15 to 85. We know that these measurements are incompatible because they are determined by a cosine squared law. Therefore, we can use these alternative transformations to achieve local Bell violations. Furthermore, if the properties of a single system are such that they can produce Bell violations in alternative measurements, then we can use twin copies of the same system to verify this behavior with joint measurements. In this case, We can use correlated quantum beams to make pairwise measurements in two identical Mach-Zehnder interferometers. In terms of my analogy with surfers, we can imagine that any quantum in Alice's setup has a partner that follows an identical trajectory in Bob's setup. Therefore, we have pairs of photons with highly correlated behavior. This is similar to throwing two coins up in the air and expecting them to land in the same way if they suffer identical microscopic perturbations from start to finish. For example, if both interferometers are in phase, then all the photons of Alice and all the photons of Bob are found in the horizontal output. However, if Bob keeps his station in phase, while Alice introduces a 45-degree phase delay, then 15% of her quanta are redirected into the vertical channel. This means that the rate of coincidence between the photons of Alice and the photons of Bob are 85% similar to 15% different. To determine the coefficient of correlation between these two measurements, we use the same old formula in which we add identical pairs of outcomes and subtract coincidences with opposite values. Yet, because we have a simple example with straightforward geometry, and because the difference in output distributions follows a cosine squared law, this calculation simplifies to the difference between the cosine squared and the sine squared of half the phase difference between the two settings. This conclusion should not be generalized because it only works under special conditions, but it will become useful later, as you will see in a few minutes. Notably, in this example, when the phase difference is equal to 45 degrees, the coefficient of correlation is equal to the square root of 2 over 2. This result is important because we obtain just the type of properties and correlations that are needed for a quantum-like Bell violation. However, we do not have any reason to invoke magical explanations. The source of this behavior is perfectly local. We adjust the position of the mirror inside the interferometer, and the effect is a change in the profile of the pilot wave also inside the interferometer. The deciding factor is the instantaneous phase difference at the moment of interaction between the quantum and the second beam splitter. Alice does not need to know what happens in Bob's experiment, and vice versa. As we saw in part 1 of this presentation, the rule is that identical objects can undergo identical transformations, in which case they can display identical properties. The distance between measurements does not matter because we can explain the result without any influences between the two stations. Hence, sequential clockwork properties are such that they can produce maximal Bell violations, while alternative transformations are such that they can produce limited Bell violations according to the cosine squared law. Though, before we move on to the final step of this explanation, we need to make an important disclaimer. Single-mode optical projections are very useful because they can help us visualize the local physics behind quantum correlations. They are easy to understand and manipulate mentally as a tool for visualizing the underlying dynamics. However, we cannot use them to reproduce a Bell experiment in full because different measurement combinations with the same phase difference do not always produce the same coefficients of correlation. Nonetheless, we can use the insights from single-mode projections to understand the features of multi-mode projections. As you will see in a minute, this will enable us to provide a full explanation for quantum-like Bell violations. The main advantage of single-mode projections is that they have stable, uniform patterns of interference that are easy to see with the naked eyes. The true nature of this phenomenon is explained by wave mechanics. However, as an intuitive aid, it is convenient to use geometrical illustrations because we only need to understand the practical implications of this setup. As you can see in this drawing, a collimated beam has geometrical features that make it look like a collection of parallel rays. This works as if we have many copies of one and the same optical vector. Yet, when these parallel rays are traced through the Mach-Zehnder interferometer, we get the same pattern over and over. To make it perfectly clear that we have the same geometrical patterns, we can use a rectangle that captures the features of the red trace. As you can see, we have a perfect optical rectangle produced by the two paths. More importantly, if we move this rectangle into a new position, we can see that the perimeter of the green trace is perfectly identical. Accordingly, when we have a collimated classical projection, we get a pattern as if many parallel rays experience the same process. In other words, if one point of the lower surface of this beam splitter experiences constructive interference, then all the points on the same side must also experience constructive interference. As a result, we do not see many interference fringes in this case. Instead, the entire surface of emission corresponds to one bright fringe. For the same reason, the entire surface of the opposite side of the beam splitter must experience destructive interference. Therefore, the entire surface will express the pattern of a uniform dark fringe. Now, let us see what happens if we replace a single-mode projection with a multimode beam. Instead of many parallel rays, we get a full continuum of wave vectors. Yet, the details of reflection at each angle of incidence are such that we cannot expect to have the same rectangular geometry for every mode. As you can see in this drawing, the green reflected path is likely to be longer than the green transmitted path, while the geometry of the red trace is antisymmetric. Therefore, we can no longer expect a uniform interference pattern across the surface of the second beam splitter. Instead, the net state of the pilot wave is perfectly chaotic. Some points are likely to be in phase, others are likely to be out of phase, with all the intermediate stages of phase difference in between. And so, the lower surface of the beam splitter will have a seemingly random distribution of points with constructive and destructive interference. Not surprisingly, the top surface will experience a similar profile. And so, it does not matter how well we tune the interferometer, because the net state cannot have visible interference fringes. Instead, we can only expect a fixed 50-50 distribution between the eastbound channel and the northbound channel. Nonetheless, we have to keep in mind that wave interference is not optional. The best concept that we have for the analysis of wave behavior is the Huygens-Fresnel principle. It implies that any amount of wave propagation, no matter how small and no matter how chaotic, is the result of microscopic wavelet superposition. So, even though we cannot see the effects of interference macroscopically, we must still assume that it is taking place. Accordingly, if we know that a large number of photons are going to be divided 50-50, we must still assume that such a division is not arbitrary. Every photon has a path that is determined by the details of its propagation under the guidance of the pilot wave. In other words, if we could magnify a small region on the lower surface of the beam splitter and freeze the instantaneous profile of the pilot wave, we should see that it has points with constructive interference surrounded by points with destructive interference. Likewise, if we could do the same observation on the flip side of this semi-reflective surface, we should see the same exact pattern except with the colors reversed. If we have constructive interference from below, then we must have destructive interference above the same spot. Conversely, if we have destructive interference on the bottom side, then we must have constructive interference on the top side. And so, if a photon arrives at any given point on the semi-reflective surface, it is never an accident what happens next. It can only come out on one side, be it in the east channel or the north channel. Yet, the outcome is always determined by the net state of the pilot wave at the exact coordinate in time and space when the photon crosses the plane of the beam splitter. With that in mind, let us try to understand what happens if we manipulate the phase difference between the two beams with the first mirror. If we use a single-mode input beam, then the effect of interference is clearly visible at the macroscopic level. When the path difference is 0, we expect 100% of radiation in the eastbound channel and 0% in the northbound channel. If the path difference is equal to a quarter wavelength, then we get a 50-50 distribution between the two outputs. In other words, half of the photons that would have emerged to the east are redirected into the north channel. Similarly, if the path difference is half a wavelength, then all the photons that would have emerged in the east channel can be detected in the north channel. In short, we have energy redistribution in a manner that is directly obvious. In contrast, if we use a multi-mode input beam, then none of these features are observable anymore. We can modulate the path difference at will at any setting that we choose, but the output distribution is always going to remain fixed at 50-50. And so, it might be tempting to assume that no interference is taking place, but this would be a mistake. As I have just explained, the fate of individual photons is still determined by the local net state of the pilot wave at the exact moment of interaction. And so, when the path difference is 0, we can imagine that we have an equal distribution of points with constructive and destructive interference across the beam splitter. Yet, every point of constructive interference on the bottom side has a matching point with destructive interference on the top surface, and vice versa. For this reason, when we delay the top path relative to the bottom path by 1/4 of a wavelength, we still have a net 50-50 distribution, but that is because the underlying process of energy redistribution is perfectly balanced. In other words, half of the photons that would have emerged in the east channel are redirected into the north channel. At the same time, half the photons that would have arrived in the north channel are now redirected into the east channel. And so, because of this equal exchange, the net distribution remains stable at 50-50. Finally, if we increase the path difference up to half the value of the dominant wavelength, then we can expect 100% of the photons to exchange destinations. All the photons that would have traveled east are now traveling north, and vice versa. This pattern of behavior has a remarkable consequence. If we can create two correlated beams and send them into a pair of perfectly identical Mach-Zehnder interferometers, then we can get perfect correlations in the distribution of coincident events. As you can see in this drawing, the macroscopic output of Alice is always 50-50, and the same is true for Bob. However, every Alice photon has an identical history to a photon in Bob's setting. If Alice's photon is emitted in the east channel, it is because it passed a point with constructive interference in this direction. That means that Bob's photon is governed by the same hidden variables and will also cross a point with constructive interference in the east direction. This holds for every other detectable photon. So, if Alice and Bob accumulate a large number of events, their records will show perfect correlations when merged together for analysis. Now, let us assume that Alice moved her mirror in just the right way to increase the path difference by 1/8 of a wavelength. This means that 15% of her photons traded places compared to Bob's photons. And so, if Alice and Bob accumulate a lot of detection events, they will observe the signature of this effect. It does not matter if individual photons arrive in the north channel or the east channel. The important feature is that 85% of the photons will coincide with identical output properties, either east-east or north-north, and the remaining 15% will be different. Yet, all this time, the macroscopic observable distributions will remain at 50-50, both for Alice and for Bob. Finally, if Bob matches the mirror displacement of Alice and both of them have a phase delay of 45 degrees, which is a path difference of 1/8 lambda, then the similarity in their behavior is restored. 15% of Alice's photons are redistributed compared to the setting with zero path difference. However, the same exact 15% of photons will have matching partners in Bob's channel that also trade places. As a result, Alice and Bob will be able to detect perfect correlations again. The first order distribution is 50-50 in both experiments as always, but the rate of identical coincidences in ideal conditions can be as high as 100%. To sum up, the pattern of interference with chaotic beams is too complex to imagine. However, the net effect of this complexity is a remarkably simple pattern. Alice can choose any setting for measurement, and the same is true for Bob, yet their coefficients of correlation will only depend on one factor. We are talking about the net difference in path length between the two experiments. For example, any choice of measurement can result in perfect correlations if Alice and Bob have identical settings. Yet, any pair of non-identical settings will have a level of correlation that is fully determined by the net angle of phase difference between the two settings. Furthermore, the amount of energy redistribution is proportional to the cosine squared of the phase difference. Therefore, the correlation between the events of multimode projections can be calculated simply by taking the difference between the cosine squared and the sine squared of the angle of phase difference. This means that we now have all the ingredients that are necessary to reproduce and to understand a quantum Bell experiment with Mach-Zehnder interferometers. For example, if we want to use the CH-SH protocol, Alice can choose two settings for measurement. A1 corresponds to an alignment with perfectly equal paths in the interferometer, and A2 corresponds to a phase difference of 90 degrees. At the same time, Bob has a choice between B1 with 45 degrees and B2 with 135 degrees phase difference. Alice and Bob can choose to make pairwise measurements in any order, yet the obvious pattern is that joint measurements A1B1, B1A2, and A2B2 will have a net phase difference of 45 degrees. This means that all of these measurements will have the same coefficients of correlation. According to the cosine squared law, the value of these coefficients is square root of 2 over 2. On the other hand, measurement settings A1 and B2 have a relative phase difference of 135 degrees. This means that a pairwise measurement with these settings must have a coefficient of correlation of negative root 2 over 2. And so, if we plug these values in the CHSH expression for a Bell experiment, we get a final result of 2 square root of 2. This is a very important conclusion. Not only did we get a value that is higher than the Bell limit of 2, we actually obtained the highest possible violation that is predicted by quantum theory. Yet, as it turns out, this is not some kind of quantum magic. This is a legitimate prediction for any combination of properties that are governed by a cosine squared rule, even if the underlying ontology is classical. To sum up, the mechanism behind Bell violations in a Mach-Zehnder interferometer is very straightforward. We just need to displace a mirror, and the pattern of wave interference at the beam splitter is automatically affected. Yet, a linear change in the position of the mirror corresponds to a nonlinear change in the pattern of energy redistribution because it is determined by the cosine squared of half the angle of phase delay. This means that different settings of the Mach-Zehnder interferometer correspond to mutually exclusive output distributions. As a consequence, we obtain incompatible coefficients of correlation between these settings, and Bell violations are naturally possible. Furthermore, if we know that the properties of one system can produce Bell violations, then we can prepare correlated systems to verify these coefficients with joint measurements. Yet again, nothing magical is happening in this case. We are merely confirming an ordinary aspect of energy redistribution. This being said, it is important to clarify that energy redistribution is a common classical phenomenon, but the propensity for Bell violations is not so common. The nuance here is that incompatible properties emerge as part of a single system. Yet, most classical systems experience energy redistribution in terms of large functional components. For example, we get the cosine squared law in some types of billiard ball collisions, but we cannot separate the momentum of balls into millions of quanta for a Bell test. More importantly, adding many systems together would not give us the right statistics for a Bell violation. The special feature of electromagnetic radiation and other quantum phenomena is that we have a dual phenomenon, comprising a wave aspect and a particle aspect. The waves operate as a system that experiences energy redistribution. Yet the particles do not collide with each other like billiard balls. Indeed, they do not even roll like billiard balls on a table. The best way to describe them is in terms of surfing entities that propagate one at a time and provide incremental information about the waves that govern their behavior. In other words, we have individual objects that express systemic properties. This is why quantum theory needs to use undetectable wave functions in order to predict the distribution of detectable discrete events. This brings us to another interesting conclusion. There is an ongoing debate in quantum theory as to whether entanglement or superposition play a primary role as a source of quantum behavior. Yet, after solving the puzzle of quantum correlations, we can see that entanglement is not really a physical phenomenon. It is an abstract connection that we can make between different measurements as a consequence of their correlation. In contrast, the process of wave superposition is essential for the explanation of quantum correlations. We have to take into account the net state of the pilot wave before we can predict the behavior of individual quanta. More importantly, this relationship is sufficient to explain the strength of quantum correlations as well as their limitations. And so, we can safely conclude that quantum entanglement is not an essential concept for quantum mechanics. Rather, it serves as an obstacle for any effort to understand it. Let us briefly recall how this problem started. In 1935, Einstein, Podolsky, and Rosen wrote a seminal paper with a big question for a title. In actuality, this paper was focused on two questions. The first one was, do we need hidden variables to explain quantum behavior? And the second one was, do non-commuting quantum properties exist at the same time? Unfortunately, these two questions were conflated as if it was possible to give one answer to both of them. Indeed, this is the same type of confusion that we saw in the case of Bell's theorem. When physical properties exist at the same time, we have jointly distributed variables that cannot violate a Bell-type inequality. So, Bell experiments confirmed beyond reasonable doubt that non-commuting quantum properties do not exist at the same time. However, we cannot use this conclusion to answer questions about local realism. It is quite natural to have incompatible properties and local realism. Indeed, when we took a closer look at Bell's theorem, we discovered that it was a false argument. I showed you in great detail that it is possible to violate Bell's inequality with two different mechanisms. We can achieve maximal Bell violations with preprogrammed sequential properties and limited Bell violations with alternative patterns of energy redistribution. And so, when we look at the two questions raised by EPR, we can see that they supported the wrong answer for the second question. Bohr was correct in his defense of quantum contextuality. However, we can also see in retrospect that hidden variables are essential for a complete understanding of quantum behavior. Bohr had no basis for rejecting the classical concept of realism. And so it was a costly mistake to turn the second problem into a debate about the first. In conclusion, I would like to add that quantum mechanics is still in its early stages of development. There are many puzzles that we still do not know how to solve. Though, let's face it, it did not help that the best solutions were banned from consideration. In any case, there are many things that we do not know, but we know enough to say with confidence. There is no magic in quantum mechanics.